In space exploration, man is an integral part of the spacecraft hardware. The human space traveler is able to serve a vital function which could not otherwise be performed. Man can make corrective control adjustments to compensate for certain electronic and mechanical malfunctions occurring within the vehicle. But what is being done to protect man in this heretofore unknown environment? Bioastronautics personnel in the Air Force Systems Command are well qualified to select, train, conduct extensive research, and coordinate operational medical support in order to ensure man's safety in all manned space exploration. The resources are many, varied, comprehensive, and are staffed by professionals of the highest scientific competence. Bioastronautics research activities span the continent. At Air Force installations and at universities and private industries sponsored by Air Force contract, professional staffs representing nearly every scientific area came together with one objective: to support and sustain manned space flight. In order to illustrate the broad scope of Air Force bioastronautics research in support of manned flights, many fundamental aspects of the overall program will be depicted. In addition, applied research associated with the factors involved during short-duration low orbital missions, during prolonged space travel, and at re-entry will be demonstrated. But before man is exposed to any facet of space exploration, instruments are sent aloft to gather information. Then biological specimens, including animals, are subjected to intensive biomedical space research. Some are launched in these piggyback containers. Many types of animals are used in the various stages of investigation, but chimpanzees are, for the most part, the optimum animal for spaceflight because of their similarity to man and aptitude for learning performance tasks. In the dry desert climate at Space, New Mexico, the Aeromedical Research Laboratory maintains a colony of primates for training and space environmental testing. In order to be utilized in space exploration, this intelligent animal is oriented to unusual environmental conditions. Doctors of veterinary medicine, physiologists, electronics engineers, psychologists, and technicians give each chimpanzee childlike care in handling, feeding. Comparative psychologists teach the animal complex performance as part of this training phase. The pre-programmed tests teach the chimp to respond to a specific symbol on the psychomotor display panel. A food pellet is the reward for correct performance. Environmental training, as well as all other phases of astronautics research, is under the constant supervision of highly specialized professionals. The chimpanzee precedes man in many phases of space exploration. Concepts of equipment must be tried and tested prior to placing man in the same environment. With this consideration in mind, Lockheed Missile and Space Company, Sunnyvale, California, working under a contract, developed a primate capsule containing a closed environmental system, biomedical instrumentation, TV presentation monitoring system. Through successful application of data gained in the chimpanzee program and efforts of the many interdisciplinary professions, life scientists are able to further their prime objective, the safety and functionality of the most complex of all subsystems, man. Prior to entry into the astronaut training program, the applicant undergo rigid physical and psychological acceptance examinations. Data collected in these tests by biomedical personnel are used not only in this evaluation, but are also stored for future reference baseline material. Initial baseline data acquisition is necessary for determining stress parameters or physical limits beyond which a human being could not safely proceed. After examining every aspect of the individual's clinical, physiological, and psychological state, the selectee is trained at the United States Air Force Aerospace Research Pilot School, Edwards Air Force Base, California. The astronaut must have adequate personal equipment which will offer protection during emergencies or when it may become necessary to leave the atmosphere of the capsule for any reason. At the Aerospace Medical Research Laboratories, Wright-Patterson Air Force Base, Ohio, special articles have been fabricated to test equipment. The final result is the creation of protective gear which far exceeds the human tolerance limits to severe external environments. Component parts such as wrist and elbow joints of full pressure suits are evaluated by anthropologists, physiologists, and by psychologists, assuring minimum detriment in human performance while guaranteeing maximum protection. Movement restrictions will be negligible and not hamper the astronaut so that he may instantly cope with any emergency situation. Simultaneous evaluations testing both and equipment are conducted in many areas of this research and development. Reaction time to stimuli is tested on this computer program input and result analyzer. Personal comfort as well as safety must be examined in the many design and positioning experiments. With assurances of adequate protective clothing, we move now into other areas of continuous experimentation. At launch, there are 4 almost simultaneous occurrences for which the astronaut must have protection: noise, vibration, toxicity, and high forces of gravity. Toxicity data gathered during launch explore the potential hazards of noxious fumes and chemicals on both the astronaut and technicians. Records of noise and vibration and separation obtained in an actual space are used as test limits in investigations. These noise factors are reproduced in laboratory experiments. The ability to perform is studied during noise exposure tests. High intensity exposure for even short periods of time can become physically intolerable for support personnel and the astronaut. In addition, these operations require continuous high communications with the astronaut, as an interfering factor must be reduced or eliminated. Vibration occurs during the high engine performance period at launch and prior to the time orbital velocity is achieved. These conditions can become so severe as physical incapacitation. Research is conducted in biomedical laboratories to determine man's tolerance to training and familiarization programs, and which tend to reduce the effect of vibration on the astronaut's performance. The effects of forces incurred at time of launch and massive ignitions of multi-stage booster engines have been thoroughly studied. Human tolerance in various body positioning experiments established on the centrifuge. Complementary Air Force-sponsored research, universities across the nation, supply of qualified scientists, and to diversified methods of approach. Again, utilizing the most effective applications of our resources, both men and equipment are integrated into a performance aircraft. Air Force Flight Test Center, Edwards Air Force Base, California. Testing under severe conditions is conducted in the X-15. Physiological instrumentation records the pilot's tolerance to the stresses incurred in flight. New miniaturized instruments located at strategic recording points on the pilot's body transmit information to a transistorized relay package situated behind the cockpit. This physiological data is then telemetered to ground stations and relayed to the Medical Control Center for instantaneous readout. Thus, both men and new miniaturized equipment are tested for performance under flight stress conditions. The second phase of spaceflight experimentation is concerned with low orbital space flights and research conducted in weightlessness. This state of zero gravity occurs when the velocity of the spacecraft counteracts the Earth's gravitational pull. Man and equipment must be able to operate in a weightless state. Training and testing procedures developed by Air Force human factors engineers who, calling on experience gathered over years of experimentation, are able to simulate some of the effects of zero gravity. At the School of Aerospace Medicine, Brooks Air Force Base, Texas, disorientation experiments are conducted in a 3-gimbaled chair, free-floating on a cushion of air. This apparatus provides 3-dimensional freedom, one of the conditions the astronaut will experience in weightlessness. Any space travel will result in long periods of confinement. Crew members must be able to withstand this psychological stress individually and as a working group. Biochemical changes which take place in man and in his environment must be examined. Changes occurring in cabin atmospheric gases are also being investigated in a test cell inside one of the pressure chambers. At the Aeromedical Research Laboratories, men and equipment undergo simulated confinement for the detection of changes in these ambient gases. Adequate oxygen supplies are an absolute necessity to sustain human life. A sensing device developed by the Air Force an insufficient supply of this vital element on a moment-to-moment basis. As man lengthens the duration of orbital missions or ventures into space, the logistic problems of providing a livable atmosphere manifest themselves to an even greater extent. Utilizing nature's own method of recycling carbon dioxide through plant life, the photosynthesis, or generation of oxygen, is produced using algae or other forms of rudimentary plant life. Another method of supplying oxygen includes the utilization of body waste to feed the algae or the photosynthetic reaction. In its ability to produce oxygen and absorb CO2, algae are also being used as a possible source of food or dietary supplement. Radiation in the Van Allen belt, solar flares, is under extensive study. Experiments using space bacteria, viruses, and tissue culture to determine the biological effect of radiation in various layers of the Van Allen. Air Force Base, New Mexico, development of a plastic man with the same composition as human tissue, scientists to accurately determine the depths of radiation penetration as well as doses without actual human exposure. Called the plastinaut, this fully instrumented is now undergoing tests in simulated exercises. When the space traveler leaves his capsule for any reason, he will be subjected to temperature variations far in excess of those on Earth. Scientists from the University of Indiana and bioastronautics are working side by side in the Wright-Patterson Climatic Chamber investigating this phase of research. Simultaneous extremes in temperature and humidity are simulated in order that various protective materials can be tested on volunteers to determine maximum safety and performance. In space, there will be no visual reference cues such as we have here on Earth. In early childhood, we learn to compare sizes of objects around us, and we are able to estimate distance. Visual indoctrination train the astronaut to orient himself in the void of space. With no atmosphere acting as a filter, extremes in light exist. Research into this field has led to the discovery of self-attenuating filters, which could have many other practical applications. Re-entry into the Earth's atmosphere poses another set of problems. The lessening of tolerance to re-entry forces from previous weightlessness is also being tested in simulated conditions. Severe buffeting will be encountered at the outer fringes of the atmosphere during re-entry. Maneuverability will be difficult in this situation. Biomedical research is attempting to increase man's ability to perform emergency functions during this critical period. Disorientation and forces of gravity will also be experienced during this phase of spaceflight. Rapid deceleration studies at Holloman Air Force Base determine man's tolerance to the forces encountered prior to or at impact. Methods are under investigation to reduce the severity of these forces on the re-entering astronaut. Instruments and protective devices are also put through a series of deceleration tests to ensure an adequate safety margin before incorporating man. Restraining couch tests determine the best methods of positioning a human subject exposed to landing impact. Escape is essential throughout the entire space mission. Tests being conducted in high-performance aircraft may prove to be the solution to this serious problem. Under investigation is a method of putting man in a capsule, which would protect him in an emergency escape situation occurring within the Earth's atmosphere. Bioastronautics activities in the manned space program do not end at the research phase, but continue throughout the entire program, extending into the operational support of all biological and manned flights. From a strategically located converted blockhouse used as the forward medical station at Cape Canaveral, monitors are in constant electronic contact with the astronaut or the primate during down, launch, and flight. Medical specialists also monitor the flight proceedings from the astronaut preparation area. This facility is on a standby basis and is prepared to render instantaneous major medical support for any occasion that may arise prior to or at the time of launch. The bioastronaut coordinates the emergency recovery force. This recovery team is of all branches of the armed forces, stationed at strategic points near the launch site, and is ready to spring into action if the advanced medical stations, such as the one at Grand Turk Island, are on a standby basis to render emergency assistance to the space traveler and as a facility for clinical examination of the astronaut following recovery in the planned impact area. This hospital facilities are easily relocated geographic sites along the space track. Bioastronautics circle the globe with medical on ships at sea and at island-based advanced recovery hospitals. We have few representative fields of endeavor conducted through the division of the life in the Air Force Systems Command. This activity requires technical disciplines of highly qualified specialists coordinating as a team with one objective: to effectively blend the intricate, complex subsystem, man, into the exacting high-performance systems of tomorrow. Every search for the protection of man in the space program is being considered and investigated by the bioastronautics personnel of the United States Air Force.